as some of you will be aware, there's been just a little bit of a stuff up with these, the lectures and the labs, in that the lab that you're doing this week is on stuff that I'm going to be, or at least some of it is on things that I'm going to be talking about this morning. So that is a consequence of the Good Friday, missing out on a lecture on Good Friday. So that's going to continue happening unless we make up a lecture. And the way in which I'm going to make up the lecture is this Friday I will try and do, I won't do 2 lectures because that'll be impossible, but I'll do the normal lecture that we would have had, and I will summarise lecture 16. I will also put last year's recording of lecture 16 on, I guess it's probably on the Moodle site, so that you'll be able to access that. But if we don't do that and play that catch-up, we're going to have this problem continually for the rest of the semester, where some people at least won't have seen the work before they're starting to do the labs, and that's not really an acceptable way of doing things. So I apologise for that, but that Friday was outside my control. So what we're going to do today is continue looking at root finding, but also start touching a little bit on optimisation, and we'll actually see how the root finding process actually comes into optimising at least very simple functions. So let's just try and remember what we did, I guess it was 2 weeks ago now, looking at root finding methods, in particular the 2 bracketing methods that we considered, the bisection method, where you start off with 2 guesses, and the critical thing in starting off with these 2 guesses is the function has to change sign between this point and that point there. If it doesn't change sign, then you can't use these bracketing methods. Okay, so the bisection method basically said, okay, if we've got 2 guesses, one on either side of the root, our next best guess is the point in the middle. Okay, and it's guaranteed to always find a root, provided you've got things on opposite sides. In actual fact, there are a couple of tricky situations where it might not work. For example, tangent, where it actually goes off and asymptotes to, say, negative infinity on this side of pi on 2, and asymptotes to positive infinity on the other. So you can actually pick 2 points there, but there isn't actually a root. Okay, so there are a few pathological cases where it won't work, but by and large, for any sensible function, it's going to work. The other method was the method of false position, and basically the algorithm behind this, in other words, the way in which you implement the method in MATLAB, is identical to bisection. The only thing that's different is the way in which you choose your next point. Excuse me, could you close the door up there, please? So that's the only difference between bisection and the method of false position. Okay, you're just using a different algorithm or a different method to find your next guess. And remember, with all of these things, in most cases, you're never ever going to find the exact root. It's only going to be very, very close. Okay, occasionally you'll just happen to luck on the exact value, but there's always going to be some kind of error tolerance in these things. So you're almost never going to find the exact value. You need to specify some kind of precision that you're prepared to accept, some kind of error that's not going to mess you around too much in what you're going to do later. Okay, for both these methods here, because you're starting off with 1 point that's negative, 1 point that's where the function's positive, you're guaranteed to find the root. However, these things can actually converge quite slowly. Now, if you've got a really simple function, it doesn't really matter. You can do 100 million iterations if you need to, and it's not going to take you any time. But if the problem that you've got is much more complex than that, where, for example, the function value might be the result of a simulation that takes 2 or 3 hours to run, and you need to do hundreds of iterations to find the root, then these methods are going to be prohibitively slow. So we need to find better methods. The other problem with those methods is we need to know where this function changes sign. If we don't know where that changes sign, we've got no way of actually starting off the algorithm. Okay, so what we're going to look at today is 3 different methods which are pretty similar, which will allow us to just use basically 1 guess for that initial value. They're the Newton-Raphson method, the secant method, and the modified secant method. And we'll see, I'm hoping you'll see today, that in actual fact, they're all extremely similar. Okay, there's only, again, like the previous 2, where there's only 1 difference, in other words, the way in which we chose our next guess, these 3 methods are almost the same. There's just 1 thing that's different between each of them. The thing about open methods is that you don't need to bracket the root. And, well, usually requires only one initial guess. Effectively, it only requires one initial guess. There's one slight modification with the secant method. And these methods, if they're going to converge, they will always converge much faster than bisectional false position. One of the problems is that sometimes they don't converge, and they diverge, they go off to infinity, or they go off to some crazy value, or you don't find the root that you're actually looking for, you find a different one. We'll have a look at some of those things in the lecture. So the basic Newton-Raphson method, we start off with the function, the black line here, and we take a starting guess, the point xi. That's going to be, we think the root's pretty close to there, and we look at the function value at that point and the first derivative of the function at that point. So the slope of the tangent to that point on the function, the slope is given by the first derivative of f of x. Okay, that's just what the first derivative is, it's the slope of the line. So based on this, we can say, well, okay, if we actually followed this tangent down from this point to where that tangent hits the axis, that's actually going to be a better guess for where the root might be. So that's the basic idea behind these three methods is we're taking a tangent to the curve, we're going to follow that down to the x-axis and say, okay, that's going to be our next guess. So if we actually look at what that looks like is, okay, the slope of the tangent here is just given by the rise over the run, so that's the function value at x minus 0 divided by xi minus xi plus 1. So that's just the vertical extent divided by the horizontal extent. That's the definition of the slope. From this equation here, we just do a little bit of algebra, it's not very complex, and we say, okay, our next guess, xi plus 1, is equal to our old guess minus the function value at xi divided by the derivative of the function at xi. And that's it. That's the Newton-Raphson method. Okay, it's really simple. So let's actually sort of step through it in a particular case. Here we have a function which I've called g of x. Our blue line here is the function, and we take some initial starting guess, x1. We draw the tangent to the curve, and where that crosses the x-axis, that's our new guess, x2. We do the same thing again. We've got to start off with x2, we draw the tangent there, it hits the x-axis at x3, that's our new guess. And you can actually see that, certainly in this case here, where the curve's curving over like that, we're actually accelerating at each step. We're getting closer and closer, even faster. x4, x5, and then finally we come close enough. Okay, now again, what does close enough mean? Close enough means that the absolute value of the function at our guess is smaller than some tolerance that we choose to specify. Okay, and that's up to us as to what we specify, what tolerance is acceptable. So let's have a look then at some pseudocode for this. Basically, to start this thing off, you need the function value at x and you need the derivative at x. That's where xi here is our starting guess. We calculate our new value, our new guess of the root, and then we just keep on repeating steps 1 and 2. So do you think you're going to need to use a for loop or a while loop in something like this? Because you're going to have to code these things up. Sorry? It's got to be a while loop because we don't know how many times we're going to have to iterate on this. You know, it might converge in 3 iterations, it might converge in 20. Okay. So taking this and expanding it out to approach a little bit more like what we might write in MATLAB, calculate those things, while, and don't forget the absolute value. This is probably the most common mistake that I see when people try and code up things like this. You need the absolute value there. While the absolute value of that is greater than the error we're prepared to accept, the precision, then go ahead and calculate the new root, estimate the new function values at the new root. See whether we're close enough. If we're not, go do it again. Okay, so this is a little bit different to the functions we did last time. So based on that little bit of pseudocode there, what inputs are we going to need into this Newton-Raphson function, and what are the outputs? Well, I'll tell you what the output is. It's the root, okay? It's pretty clear. But what things are we going to need to pass into the Newton-Raphson function? Let's go back and show you the formula again. Yeah, the precision, that's absolutely. What error are we prepared to accept? That's absolutely important. How about a starting guess? We need to start this somewhere, so we need a starting guess. There's two other things that we need. The function handle and the derivative function handle. Yeah, you probably, that's good. You're awake this early on a Tuesday morning, which is good. Okay, so the inputs are the function handle derivative, the initial guess, and the precision, and the output is the root. In actual fact, quite often too, you may want to know how many iterations that this thing takes, so you may want to output the number of iterations as well. So, to code this thing up is incredibly simple. Okay, just for the moment, forget all about all the green comments, although, of course, as good MATLAB programmers, you'll put in lots of comments so that you know what your code's doing. And I do advise you to put some in, not just because you might get a few marks for it, but because if you ever have to come back and use this later in the semester, or maybe next year if you're doing another unit that needs these things, you'll almost certainly have forgotten what you've done. In fact, even if you do one debugging session, you come back a couple of hours later, sometimes you've forgotten what you've done. So a couple of well-placed comments will really help you remember what you were trying to do and why you did things in a certain way. Okay, so the only bits of code in here are sort of basically the black lines. So here's our function header. Calculate the function value of xi and the derivative of the function value of xi, then go through our loop. While the absolute value is greater than precision, calculate the new x, calculate the new function, calculate the derivative of the function. And then once we're outside that loop, it means we've converged. And the final value of our root, which we're passing back out, is just equal to xi. Now, one of the things that, of course, can happen, and I'll show you some examples in a minute, it is possible for you to get stuck in some kind of infinite loop in here, where things just don't converge. So, as a good programmer, what you might like to do is you might want to track that. So, for example, you might put an iteration count out here and you'd say, iteration equals 1, or iteration equals 0, then increment it in here each time you do another iteration. You might say, if the iteration count is greater than 10,000, then something's gone wrong, I better exit. Exit with an error message. Okay, so that would be good programming. This is just the simple basic Newton-Raphson method here. Newton-Raphson is the most widely used method for root finding when you have an analytic function that you know the derivative of. Okay, because it generally converges very rapidly and it's pretty robust. But you need the derivative of the function. And that really is the big but with the Newton-Raphson method. Sometimes you can get the derivative, but it's not necessarily very easy to get it. And sometimes it's not possible. So, for example, if your function was the solution to a partial differential equation on some system that took hours to run, what's the function there? How are you going to take a derivative of that? The answer is you can't. Okay? So you can't use Newton-Raphson when you don't have a function that you can take the derivative of. But there are ways around that. So let's just have a look at a function I think I showed you in the last lecture. G of t is equal to this moderately complex thing here. You start taking the derivative of it. Well, I mean, this is the kind of thing you can code up in MATLAB. It's not such a big deal. But you can see that for even reasonably simple functions, you can end up starting to get quite complicated derivative functions. And as soon as things start getting complex, the possibility of making mistakes creeps in. Because, and this is really important, this derivative function actually has to be the derivative of that function. If you make a mistake down here and say you left off that 1/2, you've actually got a derivative function that's not correct. And as soon as you do that, you're almost guaranteed not to find the correct answer or to find any answer at all. Okay, so the derivative really has to be the derivative. But, as I've said a few times, Newton-Raphson does not always work. And let's just have a look at a few examples. Let's look at this function here. We start off at x0. We look at the function value, we take the derivative, we get a value x1. Go down here, you get a value out here, x2. We go up here, we come down here, we get a value across there, somewhere of x3, and we go around this loop. And in actual fact, for this particular function here, this thing diverges off forever. And the value, our estimate of the root just gets worse and worse and worse. It's also possible that for these things here that you can actually get what's called a limit cycle. If the function is just right, this thing will just go round in a loop like this. So it'll never get closer to the root and it'll never get further away from the root, but it won't converge. And so that's another possibility. This is another example here where you've chosen an initial guess round here. You start off at x0, you go to x1, to x2, to x3. So we're sort of jumping around all over the place and still not converging on the root. Another case when you've got multiple roots. Okay, we start at x0 here. We go across here to x1, and this actually takes us across into a different part of the curve. So actually, say we're trying to find that root there. After the second iteration, we zipped across here. We've actually skipped over a couple of roots. And likely with this one here, we might find some kind of root across here. So that's the other problem with Newton-Raphson. In fact, the three methods I'm going to talk about today is that you're not necessarily guaranteed to find the root that you're after. Okay? So you've got to make a good choice of your initial guess. And one of the things that I think you can see by looking at all three of these curves here, actually no, it's on the next one probably best. You right there? Good. If you're making an initial guess where the first derivative is close to 0, you can see automatically that if that derivative is 0, then you'll go off to infinity. You'll never cross the axis, okay? So if the slope's 0, you're stuffed right from word go. But if you choose a point where the slope is almost 0, you'll end up going a long, long, long way away from where you started off. So that's kind of like, that's a bit of a test. Is the slope of my function close to 0 or is it not? So one of the things about Newton-Raphson is it's good to have a good first guess. And you can't always do that, of course. And functions can sometimes be pathological like this, which means that you can't get what you're after. But a good first choice, if you can do something, and one of the best ways of doing that, of course, is if you can, is to plot the function and just eyeball it and say, well, the root's somewhere near pi. I'll just put pi as my initial guess, or it's near 3 or 2, whatever it is. Okay, so as we've said all along with Newton-Raphson, actually I'll stop there. Is there anything about Newton-Raphson that I've tried to explain unclear? Is the basic concept simple? Do you understand it? Do I need to go back and do anything? I know people are reluctant to actually put up their hand and say, I don't understand, but it's probably better that you do it now rather than later. Okay, no takers? We'll go on to the secant method. So if we don't have a function that allows us to understand what the derivative is, or to actually pass that derivative in, how are we going to approach this? So the secant method is one way of doing that. In the secant method, you actually do need two starting guesses. Okay, but they do not have to bracket the root. They can be any two guesses at all. In fact, you're probably better off starting two guesses that are pretty close together, and that'll become apparent when we consider the next method. But in the secant method, instead of taking the derivative at a particular point, we take 2 points and we use the chord, or the secant, between these 2 points. So in the previous method, we started off here at x, well, in this case, xi minus xi, we called this one xi last time, but xi minus 1. We drew the slope because we knew what the analytic value was. In this case here, we're going to say, well, we've got a previous guess, xi minus 1. We've got our current guess, xi. I'm just going to draw a straight line between these 2 points, and where that line crosses the axis, that's going to be my new guess for the root. So you can see that this is an approximation to the derivative. It's not really a very good approximation, but if these 2 points are actually close together, it's not too bad. Okay? But the secant method follows exactly the same logic as the Newton-Raphson method, except you need 2 starting points. That's the only difference. Okay? But they don't have to bracket the root. And in actual fact, if you actually look at, okay, the slope of this line between these 2 points, xi and xi minus 1, that's just the function value, difference in function values divided by the difference in x values. And if you just rework that, remembering that f of xi, it's xi minus, sorry, I'll withdraw that comment. I've got that wrong. So we basically, just between these 2 points here, we have a difference in function values, f of xi minus 1 minus f of xi, and we've got a difference in x values, and that's the slope of the chord, and we then use that to calculate the x-intercept. And we come up with xi plus 1 equals xi minus this thing here. Now if we look at these two terms, f of xi minus 1 minus f of xi divided by xi minus 1 minus xi, that's like a finite, it's like an approximation to the derivative. It looks a little bit like a derivative. But this process here is the process you use to calculate the new guess. Okay, so two new guesses, and basically the same deal, and I'll see whether I can get the MATLAB. Okay, yep, okay. So in this particular case here, we've chosen our 2 points. We draw the straight line to them, and this point here becomes our new guess. We then use the previous point, xi, and the new point, xi plus 1, to get the new point, xi plus 2. Okay, so we're always dropping off the first point, or the oldest point that we're using. Okay, we've drawn that straight line. Here's our new guess. We now use those 2 points to get a new guess, and you can kind of like see how things are converging quite rapidly on the root, especially as we get closer to it. And the final 2 points, and then eventually we get there. Okay, so the process, the algorithm, is identical to Newton-Raphson. It's just the way in which we calculate the new guess. That's the only thing that's different. Okay, so I've been through this basically. So, a little bit different in terms of the inputs and outputs to the secant method, because we no longer have a function derivative. But how many input parameters do we need, do you think? 4. Yep, you bet. And so we still need the function handle the equation. We now need 2 initial guesses. Okay, but there's no necessity for these to bracket the root. And in actual fact, if you go back and look at the method of false position and the secant method, the methods are identical except for the necessity for bracketing and the way in which we choose the limits. Okay, in the secant method, we just choose the last 2 guesses. In the false position method, we choose one where the function value is negative and one where the function value is positive. But the actual formula we use to calculate the new value of the root is the same. So there's a lot of overlap between all of these different methods. Okay, so function value then, pass in the function handle, are 2 guesses and the precision that we want. Always got to remember the precision. The next method is called the modified secant method, and it looks almost identical. But now, instead of using the last 2 guesses of x, in other words xi minus 1 and x, we're using our current guess, which is xi, and we're just going to add a small delta to it. And in actual fact, you could subtract a small delta if you wanted to. It wouldn't make any difference. Effectively, what we're doing is we're just saying, okay, here's our guess. I need to make an estimate of the derivative using, I haven't actually got the formula written here, basically using what's known as a finite difference approximation. In fact, if you remember your calculus back from when you first learned calculus, the definition of a derivative was the function value at x plus delta minus the function value of x divided by delta, take the limit as delta goes to 0. Okay, so effectively what we're doing is we're putting that into practice with the modified secant method. We're just choosing a small delta, and really we can make this as small as we like. We can make it 10 to the minus 6. And in actual fact, the smaller you make delta, the closer you get to the analytic derivative of your function. Okay, so taking these 2 points, xi plus delta, or delta xi as I've written here, we do exactly the same thing that we did for the modified secant method. Okay, so our new value of x is equal to the old value of x minus delta times the function value of x divided by the difference in the function values. So these 2 terms here and this delta x here are just like the inverse of the derivative. So it looks, if we go back to the Newton-Raphson method. Oh, gee, if I can finally get there. That's exactly what we've got here. It's the function value divided by the derivative. So the modified secant method's the same. We're just calculating the derivative in a different way. We're using what's known as finite differences. And again, for the modified secant method, now you've got slightly different inputs. The only thing that's really different is now you need the perturbation that you're going to input. Okay? And you might want to choose that based on the range over which you want your function to operate. So if you're trying to find a root over a really tiny domain, you obviously need to make delta much smaller than the domain size. Okay? If your delta's 0 to 1 million, delta can be much bigger. Well, at least initially. So what's the difference between these three methods? Really, it's Newton-Raphson, we use an analytic estimate of the derivative. The secant method, you make an estimate of the derivative using the last two guesses in your algorithm. The modified secant method, you use a derivative estimated on your last guess and some small delta, some small parameter that you want to put in. From the point of implementing these things, they're exactly the same. So let's just maybe go and have a quick look at, say, the modified secant method. Okay, so the modified secant method looks like this. Function value at xi is equal to the function value at xi. Fx plus delta x is just the function value at xi plus, this has been done in a certain, this is basically, this thing here is dx in the previous thing. Then we go through the loop. Okay, while the absolute value of the function is greater than the precision, in other words, we haven't converged yet, we need to do another iteration. Your old value of x is equal to xi. The new value is just equal to this thing here, which just looks like the function value divided by the derivative, but now calculated using this finite difference type approximation, which is f of x px minus f of xi divided by delta x, which is this perturbation times xi here. That's all just updating the animation. So in actual fact, if we run this thing, we'll see we get exactly the same answer. So here's our initial guess. There's that tangent approximated using that finite difference approximation. Here's our new guess. There's our new guess. Then finally we hit on the root. Okay, so the only difference is the way in which we calculate the derivative. The rest of the algorithm between these three things is identical. So if I gave you a Newton-Raphson code and said, I want you to convert this to a secant method code, you'd only have to change a few lines in there. Likewise with a modified secant. So those are all things that you can code up yourselves. And in fact, I think you probably need to code them up yourselves. But there are also, as with MATLAB, there are also inbuilt functions that you can use. Okay, the key thing is that there is no one method that is best when it comes to doing this thing, coming to find the roots of equations. The MATLAB function f0 uses what it thinks might be the best method depending on what equations and what information that you're giving it. Okay, so f0 is something that you can use, and hopefully you're more likely to get a better result than if you write your own code, or at least it'll be maybe more robust. So the syntax for f0, in other words, the way in which you have to call it, is you call it with a function handle and one initial guess, or a function handle and a bracket. In other words, I know my root lies between here and here. Okay? There are a few little few little subtle things here that we need to watch out for. So let's have a look at this function here, a really simple function, x squared minus 9. If we pass in the function handle, x squared minus 9, we pass in an initial guess for the root of minus 4, we'll find the root here at minus 3. Okay, because what we're doing is effectively we're drawing a tangent. Well, what it's going to do, it's going to use something like Newton-Raphson or modified secant or something like that. It's going to draw the tangent and it's going to home in on this root down here first. Okay, and it may be that for whatever reason it was the one across here that you wanted. So what you've done is you've chosen a bad initial guess for what you're trying to do. Likewise, if we start across here, our initial guess for the root is x is equal to 4, will converge nicely onto that point there. So the initial guess is important. So having some understanding of what you're trying to do before you go off and do it is really important. And I guess that's just a general comment for anything that you're doing with programming. Understand what you're trying to do first so that you make good guesses. You make good initial conditions. So that's if we then choose use f0 and choose our initial starting point as 0, which is this point here. Now remember I said that can be potentially quite dangerous if you're using Newton-Raphson because you're never going to get anywhere. Clearly f0 is actually going to work in this case here, so it's going to do something a bit smarter. It knows, oh wait a second, I've got my derivative 0 or close to 0, I'm going to have to do something different. Okay, now to be honest I have no idea what algorithm it uses to decide how it's going to do things, but if we pump in 0 here, in this particular case, it's going to find the negative root. Now, why did it find the negative one and not the positive one? I don't know. And you'd need to actually get inside that code and actually have a look to see how it made its decisions to figure out why. So, again, if you wanted the root here at x is equal to plus 3, and you just made an initial guess, a clumsy initial guess, or a guess without thinking, oh, I'll try 0, you may end up with a value that's not what you want. So you've always got to be careful and try and understand what it is that you're trying to do. The other thing, that I said that there are two different ways of calling f0. One is to pass in a single value. The other is to pass in 2. So if we do f0, again our function x squared minus 9, and we pass in a bracket now of 0 to 4, we're telling it, I want to find the root that's this one here. So we're giving it a bracket. Unfortunately, if we pass in, I want to calculate the root between minus 4 and 4, when we pass the bracket that goes in from here to here, we actually end up with an error message, sorry. So it hasn't worked. And the reason for that is, it's using some kind of bracketing method here because we've passed in a pair of points. But like all bracketing methods, the function value has to change sign. And if we pass in minus 4 and 4, the function values are both positive. So it, for whatever reason, it's not smart enough to figure that one out and try and do something else. So passing this thing in won't work. You'll get an error message. So f0 isn't foolproof either. Although I'm sure I could figure out a way of making it so it would work for that one there. Okay. Yeah, let's have a look at this example here. So what we're just going to have a look at here is comparing root finding methods for this particular equation here, cos of x squared plus 5 divided by x to the 4th plus 1. Okay, we choose an initial guess for bracketing methods in this range here. For open methods, we choose a value of 2. We want a precision of 0.1%. And perturbation here is 0.01. That's the delta that we're using in the modified secant method. We also need to calculate the derivative of this if we want to use Newton-Raphson. And so if you can go through this, I actually think there's actually a minus sign missing here. But that's the derivative of the equation. Pass all these things through. Look, I'm not going to go through each one of these things individually. That's just a bit of MATLAB code here. Let's just have a look at what this function looks like. It's a slightly strange looking function. It comes across here, it dips down, it dips up, it's got another little dip in the middle, it goes down, it gets up. It's nice and symmetric at least. Okay, but in this region from minus 5 to 5, it's got 4 roots. So remember, we chose a bracket from point 8 to 2.2, and we chose an initial value of 2 for the cases where we only needed one guess. And if we just go through and look at all of these various different methods, we look at the total number of iterations that each of these different methods takes, and we look at the percentage error. Now, it seems that F0 gives an error that's spot on, well, at least to machine precision. Bisection took 8 iterations, false position took 4, Newton-Raphson secant modified secant, 5, and modified secant 6. So in actual fact, they're all taking fairly similar amounts of work. Okay, so for cases like this, there doesn't seem to be a whole bunch of difference in using these different methods. For other cases, you can actually see enormous differences. Okay, especially if you start off with bisection for a very broad range, just halving that interval multiple times to get even close sometimes can take a lot of iterations. So if you start off with a very large initial guess. Okay, but it's for this case here, and this is a moderately complex function. Certainly looks like it's got a whole bunch of different stuff going on. All of the methods seem to work pretty well. Okay, so you can use most of these methods most of the time. Okay, so that's everything that we're going to do on root finding. So the key thing to remember about the three methods that we went through today is they're almost the same. The only thing that's different is the way in which we estimate the derivative. Okay, but the whole idea is to make an estimate of the derivative and see where that slope, where that line, which has the slope of the derivative, crosses the x-axis, and that's the new guess. We can do other things, however, with root finding. In fact, one of the most important things that you're going to have to do throughout your engineering degree, and undoubtedly when you get into the workforce, is some kind of optimization. Okay, by optimization, I mean here, well, what's the maxima, or sometimes what's the minima of a function? How can we maximize our profit for the amount of effort that we put in? How can we maximize the strength of the bridge at the same time as minimizing the weight of the steel that we put into it? Okay, so these problems is all about optimizing something, getting the most out for putting the least in. Okay, and this happens all the time in design kind of problems. And optimization problems can often be recast in terms of finding the root of the derivative of the function. So if we've got some function here, f of x, and we want to say, well, where's the maximum value of f? That's what we're trying to find. That's the optimization process, effectively. Well, the maximum and the minimum is going to occur when the derivative of the function is equal to 0. So maximizing it or minimizing it is equivalent to finding the root of the first derivative. Okay, now whether or not you get a maxima or a minima, you need to figure out for yourself as to what you've actually found. But often that'll be obvious. So optimization is in some sense the same as a root finding problem, but now you're operating on the derivative of the function you're trying to maximize. Okay, so that concept is one that is going to keep on coming up in your degree. So let's have a look at a really odd example, to be honest. So an object, like a bungee jumper, he's an object, not a person, can be projected upwards at a specific velocity, and he'll be subject to some kind of drag. Okay? It turns out that if you want to whack this into, now he's not attached to the bungee cord here, he's a free-moving bungee jumper. It turns out you can actually solve quite a simple ordinary differential equation to figure out that what the bungee jumper's height as a function of time is equal to. It's equal to his starting position, and there's a term down here to do with the drag term, and there's a term down here, the acceleration due to gravity, where these parameters are various different things. Let's just plot the altitude as a function of time. The curve looks like this. So he starts at an altitude of 100 meters. What's his initial velocity? We don't actually know for this particular example. For some reason, he's shot up in the air. He's got drag acting on him. He gets up to the top. Gravity's acting on him, and he comes back down again. What's his peak elevation? How high does he get? Well, his function of height as a function of time is equal to this equation here. Okay. we know his peak, well, just based on this curve here, and this is where we've done something a little bit smart, we've plotted something so that we can see, well, is it going to be 0 seconds, is it going to be 100 seconds? Well, we know it's going to be around about 4 seconds, and his altitude's going to be around about 190 metres. Okay, so how do we actually do that? Well, we go back to that function z of t that we had before. We take its first derivative, and then we use some kind of root finding algorithm on that first derivative. Okay, so in that case we could use Newton-Raphson because we've got a function and we can take the derivative of that function. Or we could use bisection. We know it's got to be between 0 seconds and 10 seconds. Any of those methods. And we would actually then end up saying that his maximum height was achieved at about a 4-second time period. 4-second time, altitude to 190 metres. That's a bit of a simple example. Let's have a look at an example that in some ways is a little bit more real. If you look at the flow over an airfoil, okay, there are two components to that force. There's a drag force, in other words, the force that's pushing it backwards if it's moving forwards, and there's going to be a lift force. It's either going to lift it up or push it down, depending on which way the foil is pointing, and which way the flow is coming. Let's just have a look at the drag force by itself. The drag force, in actual fact, has two separate and different contributions. One is called the skin friction. Effectively, that's the viscous stresses acting on the surface of the foil. And there's what's sometimes called a lift drag. It's a pressure drag kind of a force. And if we actually look at how this functional form of this for a particular airfoil, we find that the total drag here is represented by the following equation. So the drag as a function of the velocity is equal to some coefficient, 0.01, times sigma, which is the ratio of densities at altitude and sea level, times v squared, plus this other term, which is like a 1 on v squared term. So we've got two completely different terms, v squared and a 1 on v squared term. These other things here are just coefficients that are applicable to this particular airfoil. They're not generic in any way. What's important is the v squared and the 1 on v squared. So if we actually plot that, this green line down here, so we can see what's going on, is the skin friction, and it increases from nothing and gets higher and higher and higher. The lift drag is the red curve here. It starts off quite high and it comes down. But if we add these two things together to look at what the total drag is, we see we end up with a curve that comes down, has a minimum, and then goes back up again. Okay, the key thing here is that the total drag has a minimum. And so we're ultimately going to be interested in what that minimum is. And what that's saying is, if we fly at this particular speed around here, we're going to have the minimum drag. If we go faster or if we go slower, the drag's going to be higher. So, as an example of how you might want to use something like this, that's exactly the question I'm going to ask. At what velocity should we fly to achieve the minimum fuel consumption? Okay, we know that the drag force on this airfoil is equal to this function here. The first thing we need to do is we need to assume that the fuel consumption, minimum fuel consumption corresponds to minimum drag. So you need to make some assumption there that the thing that you're trying to maximise is directly related to something that you can measure. Okay, making that assumption, which I think is probably a pretty reasonable one, the optimisation corresponds then to finding in this case, the minima in d of v, which is the same thing as finding the root of the derivative of this expression with respect to v. So if we take the derivative of this with respect to v, we end up with this equation down here. We then need to find the root of this equation. Now, if you just look at this equation, you can actually just solve that analytically, right? You can just say, okay, when does 0.02 sigma v equal 1.9 w squared divided by sigma v cubed? You can actually do this one analytically. It's not very difficult. Generally speaking, that's not the case. Generally speaking, you won't have something where you can easily calculate, easily solve this equation here, and then you'll need to bring in your root finding expertise. Okay. Actually, one thing that I had actually forgot to mention earlier on, and is really, really important when you're doing root finding, it's always a good idea, once you think you've found the root of your equation, to substitute it back in to see whether you get a number that's close to 0. Okay, that might sound like a really obvious thing to do, but even I forget to do that sometimes. Oh yeah, I found the root, I'll just go off and do what I want. that little proof of that you've actually done everything right is extremely valuable, and I recommend that you always do it. So if you think you found it, just plug it back into the original equation. Do I get a value that's close to 0? Important thing to do. Okay, so what have we covered today? What do you need to take home? You need to understand Newton-Raphson secant and modified secant method, understand how they're different, but importantly, how they're almost the same as well. Okay, we've also been through the F0 function in MATLAB, and I've given you an example which wasn't a pipeline, which was a lifting airfoil. Remember, on Friday we're going to try and get through a whole bunch of stuff to try and make up for our lost lecture.